Hello everyone, and welcome to numerical analysis. And in this video we're going to talk about numerical differentiation. Basically, or specifically, we're going to talk about Newton's divided differences. Alright, so let's get into it. So the concept behind this is a polynomial approximation using different methods in calculus, much like Taylor's polynomials are implemented. So this uses predefined points on both x and f of x to approximate a specific value. Let's consider an example here. So consider the following data points generated by f. So we have points here. We got x, which is 0 0.2, 0 0.4, and 0 0.6, and then we've got f of x, which is 12.18249, 3.49034, and 2.30098. So we're asked to approximate 0.5 using Newton's divided differences. So what are we going to get? Okay, so we have our data points there, and we also have our data points there. So this table is just for illustration purposes only, and in this table is for actual solving. So basically, how to use or how to solve Newton's divided differences. We're going to use this formula. Sorry. And the formula states f of xn plus 1 minus f of xn. So if this is our f of xn, this is our f of xn plus 1. So we're going to get this guy minus this guy. Divide by xn plus 1 minus xn, meaning this guy minus this guy. So the same goes for if you want to find for this one here, right? So let's try finding for 0.4 and 0.2. So f of 0.4 is basically 3.9034 minus f of 0.2, which is going to be 12.18249. So if we were to do our calculations there, we'll find that this guy here, when you divide the operations of this one and this one, you get negative 43.46075. As shown here below on top here, and we get 2.3099 minus 3.49034 divided by 0.2. When you subtract this guy minus this guy, you get 0.2. You subtract this guy minus this guy, you get 0.2 as well. And when you subtract this one from this one, you get this value, and then when you divide everything, you get this value. So we see that there's a connection here. We have these two are meeting up with this point, and then we have these two meeting up at this point, with this is the initial value. Okay, so now that we have our points, which is negative 43.46075, and we got negative 5.9468, we're going to use this formula again, and then we're going to say f of xn plus 1, so meaning this guy, plus 1, which is this one, minus f of xn, which is this guy as well, subtracting xn plus 1 minus xn. So now notice that we are, for our x values, we are going to use these arrows to actually help us navigate what x values we are going to use. So because we are using this top one here, so we're going to go on top like that, and we're going to recognize the x value that is associated with this guy. So we're going to say 0.2. So 0.2 is going to be our xn in this scenario. And we look at this value because it's at the bottom, we're going to go at the bottom. So we say negative 5.9468, and the x value that is going to be used to find the value is going to be 0.6. So in this case now, we're going to say negative 5.9468 minus negative 46075 divided by 0.6 minus 0.2. So we have this equation there, and for us to find the actual value, we see that we get 93.784875, and we have that type of relationship there. And because we don't have anything else that we are subtracting or doing anything there, so we just have this type of relationship and no third iteration whatsoever. So because we are done with our iteration table and we have found our first iteration, our second iteration, we're going to introduce some data points known as A naught, A1, and A2. These are very important data points because they will help us actually find the value we are looking for. So the actual formula is f of x is equals to a naught plus a1 multiplied by x minus x naught plus a2 multiplied by x minus x naught multiplied by x minus x1. And then if we were to substitute our values, we're going to get a naught is going to be 12.18249, and then a1 is going to be negative 43.46075 multiplied by all these values. And now we were told that we should look for 0 0.5 of this equation. So wherever x is, plug in 0 0.5. And once you do your mathematics correctly, you'll get an approximated value of 1.95781125, and so on and so forth. This is basically the general steps of how to do everything with Newton's divided difference. Very easy, and the exact steps that I've gone through are the exact steps that you have to go through as well, because that's all there is to um, Newton's divided difference. Let's look at another example that closely approximates the value to what it actually is. So consider the following data points generated by f, and we have data points 0 0.2, 0 0.4, 0 0.6, 0 0.8, and 1. And we have f of x, which is 0.31, 0.65, 0.94, 1.32, and 1.46. So we are asked to approximate f of 0 0.5 using Newton's method. So now, I want you to look closely and say 0 0.5 is situated between 0 0.4 and 0 0.6. Well, Newton's divided differences helps us approximate a value that is within this given interval or within this given data points here. So if we were to approximate 0 0.5, it should be a number between 0.65 and 0.94. So any number between these two values is what your actual answer is. Let's look at this. So our solution could be we have 0 0.2, 0 0.4, 0 0.6, 0 0.8, and 1. And since we have all these data points here, using the same formula here, we say 0.65 minus 0.31 divided by 0.2, we get 1.7, and then we go 0.94 minus 0.65 divided by 0.2, we get 1.45. 1.32 minus 0.94 divided by 0.2, we get 1.9, and then the same thing, 1.46 minus 1.32 divided by 0.2, we get 0.7. And then you get this type of relationship that's there, and you have that those values for the first iteration. But we still have values that can be further divided. So we have to do those. We get 1.45 minus 1.7 divided by 0.6 minus 0.2, which is 0.4. And then once we have our 0.4 there, we get our value negative 0.625. And then when we get 1.9 minus 1.45 and divided by 0.8 and 0.4, we are going to get 0.4 there, and then we're going to get 1.125. And if you do the same formula over and over again, we're going to get negative 3. And if you do the same with everything here, the interval changes for x, of which now we're going from 0.2 to 0.4, and now we're going to 0.6 now. So we're saying 1.125 minus 0.0625 divided by 0.6, we get this value here. And then when we say negative 3 minus 1.125 divided by 0.6, we get negative 6.875. And then now the final boss battle here, we have 2.916, which has been subtracted by negative 6.875 there, divide by 0.8, and then we have negative 12.239625, and then we have that type of relationship there. Okay, so now we have our data points. We have A0, A1, A2, A3, and A4 for our fourth iteration there. And then now we're going to plug it into our equation there. So notice that we start with A0 plus A1 x minus x naught plus A2 x minus x naught multiplied by x minus x1 plus A3 multiplied by x minus x naught, x minus x1, x minus x2, and so forth. And for A4 we have x minus x naught, x minus x1, x minus x2, and x minus x3. And then if we plug in our values and our data points there, we'll get something like this. And because we're looking for 0.5, we plug in 0.5 of this equation here. And then we plug in something like that. And then if you do your mathematics correctly, you will get something in this line. So f of 0.5 approximates 0.7814833337. So now I want you to look at something here. Our value that we have found is closely approximated within the region of where we ought to find this value, right? So 0.4 is 0.675, and then 0.6 is 0.94. So automatically, we say 0.5 should have a value between 0.78 and something like that. So we have our f of 0.5. So Newton's divided differences helps us find our y value when you have been given an x value to solve for, which approximates the range between where we want to find our actual value. As we can see that 0.78 is greater than 0.65, which is 0.5 is also greater than 0.4, but it is also less than 0.6, meaning the value that we find here should be less than f of 0.6, which is 0.94. And we have something that closely resembles this equation. So whatever value you find here, so long as it is between 0.65 and 0.94, so long as it is between these 2 points there, your answer will 100% be correct. Alright, that's enough for Newton's divided differences. And if you have any queries, please make sure to inquire, and you can comment down below, and I will get to you as soon as possible. Take care.